All right, so we also talked a little bit about acid-base reactions last time. So what else do we know about acid-base reactions? Acid-base reactions are double displacement or exchange reactions in aqueous solution. And acid and bases are things that you've probably heard of already. So there's lots of acids in foods. There's citric acid in lemons, and acetic acid is vinegar, which you probably use in a lot of cooking. And then household materials are typically bases. So cleaning products like sodium hydroxide and ammonia are very common cleaning products in your house. All right, so, but what does that mean? What is an acid and a base scientifically? So there are many ways to define acids and bases. In one definition, the easiest of the definitions to try to remember is that an acid produces hydrogen ions. We also call these protons because a hydrogen atom contains no neutron and only one proton. So a hydrogen ion is just a proton. All right, when it's dissolved in water, that's what happens. An acid dissolved in water produces hydrogen ions. When a base is dissolved in water, it produces hydroxide ions in the solution. So that is one definition. Another definition, slightly different, is that bases react with hydrogen ions, also called protons, and can be described as proton acceptors. So sometimes the base doesn't produce hydroxide ions in solution, but if it does react with the hydrogen ion to form typically water, then we call it a proton acceptor, and it is also considered a base. All right, so another thing to know is that acids and bases are electrolytes. Not always strong electrolytes, we'll get to that in a minute, but electrolytes that produce some hydrated ions in solution. All right, so we might have also mentioned that an acid-base reaction can be called a neutralization reaction. That's because the reaction often results in neutral solution. So it usually produces water, and water has a neutral pH, so that's how you can try to remember neutralization. So sometimes the question might be written as how much acid do you need to neutralize this base? So that just means the acid and base are reacting to form water. All right, so here's an example. We're looking at nitric acid and sodium hydroxide. So when nitric acid, which is an acid, reacts with sodium hydroxide, which is a base, we form water and a salt. So a salt is just an ionic compound that consists of a cation that came from the base. So our sodium came from our base, and an anion that came from the acid. So our nitrate came from the acid. And you can see this is a double displacement reaction because the nitrate displaces the hydroxide in our sodium hydroxide, forming sodium nitrate and water. In this reaction, you can also see that sodium hydroxide acts as a proton acceptor. It combines with the proton to form water. So our OH combines with our H to form water, which is H2O, or sometimes might be called HOH because we added a proton to a hydroxide. All right. So what did I mean by strong and weak electrolytes and acids and bases? So nitric acid is a strong acid. That means it's a strong electrolyte. It ionizes fully. It ionizes 100% in aqueous solution. Acetic acid, on the other hand, is a weak acid. It does not ionize completely in solution. So you can see in our reaction here, I'm sorry, that should not be sodium chloride. that should be nitric acid. And it's forming a proton and the nitrate ion. And it's 100% ionization for nitric acid. All right, and then acetic acid is down here. We're forming a proton as well and an acetate ion, but we are not 100% ionizing. It's only partially ionized. So this is just what we learned with strong and weak electrolytes. So weak acid does not completely dissociate. A weak acid, you'll find some protons, you'll find some of our anions in solution, but you'll also find some completely intact acetic acid molecules. Whereas when you put nitric acid in aqueous solution, you get only the ions. There will be no nitric acid technically left in the solution. All right, so what do you need to remember? What are strong acids and what are weak acids? So the only strong acids, you need to remember, the only strong acids that exist, in fact, are your halogens, except for fluorine. So chlorine, bromine, and iodine mixed with hydrogen. So hydrochloric acid, hydrobromic acid, and hydroiodic acid are strong acids. And then we also include nitric acid, sulfuric acid, and perchloric acid. So those are the only 6 you would need to remember that completely dissociate in aqueous solution. All other acids, anything else that ends in acid, is not going to completely dissociate. So a lot of your weak acids are going to be organic molecules, so carbon, hydrogen, and oxygen molecules. Citric acid, oxalic acid, acetic acid, these are all weak acids. And then you also include hydrofluoric acid, phosphoric acid, and carbonic acid. And so as long as you remember the 6 strong acids, you won't need to remember what the weak acids are. It's just everything else. All right, so what more can we find out about acids? Some acids produce more than 1 mole of hydrogen ions per mole of acid. An acid that produces only 1 mole is called a monoprotic acid. So we saw this term in section 9.5. And I apologize for showing you that term before defining the term, but a monoprotic acid produces only 1 mole of hydrogen ions per mole of acid. There are diprotic acids and triprotic acids, however. Sulfuric acid and carbonic acid are 2 examples of diprotic acids. They produce 2 moles of hydrogen ions per mole of acid. That's where our di prefix comes from. So you see H2SO4 has 2 hydrogens in its formula. So it can lose 1 and form this anion, or it can lose both and form the sulfate anion. Same thing with carbonate. It has 2 hydrogens in its formula, so it can form 1 proton in solution or 2 and form the carbonate ion. Phosphoric acid, on the other hand, is a triprotic acid. It forms 3 moles of hydrogen ions per mole of acid when it dissociates in water. So you see there's 3 hydrogens in the formula, so it can produce 1 and this hydrogen phosphate ion. It can produce 2 and this hydrogen phosphate ion, or it can produce all 3 and the phosphate polyatomic ion by itself. So if you ever see something that says monoprotic, diprotic, or triprotic, that's what that means. It's how many hydrogen ions are produced when it dissociates in water. Bases are also characterized as strong or weak, and all common strong bases are hydroxides. So we have lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide, all hydroxides that we've probably seen in the last couple sections. And these are all strong bases. If it has hydroxide, it's a strong base. If it doesn't, it's a weak base. So weak bases include nitrogen atoms typically. So ammonia is a weak base. Trimethylamine is a weak base. Ethylamine is a weak base. These all contain nitrogen. Now that's not to say that every weak base will contain nitrogen, but mostly if you see a nitrogen atom and you see this reactant reacting with an acid, then you know it's a weak base. And if you see hydroxide, you know it's a strong base. So when added to water, strong bases act as strong electrolytes and they're ionized completely, just like strong acids. So sodium hydroxide, for example, forms hydrated sodium and hydroxide ions in water. And it's 100% ionization. You won't have any sodium hydroxide technically left over. It will all be ionized. When added to water, weak bases also increase the hydroxide ion concentration, but they do so by reacting. So we increase the hydroxide concentration by producing hydroxide, as you see here with sodium hydroxide. Weak bases also do this, but not by dissociating, by reacting with water. So you can see here with ammonia reacting with water, the ammonia and the water molecule react to form the ammonium ion and the hydroxide ion. So we gain a hydrogen from the water and you're left with hydroxide. So we did increase the hydroxide ion concentration, but we did not do it by breaking apart this ammonia molecule. We added a hydrogen to it to make it an ammonium ion. So, like a weak acid, a weak base is a weak electrolyte. It does not completely ionize. So, if you have a solution of ammonia in water, most of it is going to remain ammonia. Only 1% will react to form the ammonium ion. All right. So we can also write net ionic equations with acid-base reactions. So the net ionic equation for a strong acid and strong base reaction is written by first writing the completely ionized equation, just like we did with precipitation reactions. So consider nitric acid reacting with sodium hydroxide. So nitric acid and sodium hydroxide are both strong acid, strong base, so they're strong electrolytes. So they fully dissociate into our proton, our hydroxide ion, our sodium ion, and our nitrate ion. And that's what you see down here in our reactants. These are all ions. And because it's an acid-base reaction, we form water, but our remaining ions, sodium and nitrate, combine to form sodium nitrate. But do they really? No, because sodium nitrate is a strong electrolyte. It is a soluble compound. Both parts of it are soluble. So we don't form this. We keep the sodium and nitrate ions by themselves. So that makes them spectator ions because they're the same on both sides of our reaction. So when we get rid of our spectator ions, we get the net ionic equation, which is actually the same for almost all strong acid and strong base reactions. It's just a proton mixing with hydroxide to make water. This is going to be the same for almost all acid-base reactions, ABRs. The net ionic equation for the reaction of strong acids or bases with weak acids or bases is different. The net ionic equation for the reaction of strong acids or bases with weak acids or bases also involves writing a completely ionized equation and identifying any spectator ions. For example, consider the reaction of HCl with the weak base ammonia. So we have HCl and ammonia, and we've seen before that ammonia will act as a proton acceptor and accept the hydrogen ion to form, or the proton to form the ammonium ion. All right, so when writing the equation in its completely ionized form, then we see that hydrochloric acid is a strong electrolyte, a strong acid, so it completely dissociates, while ammonia is not, it does not dissociate, but it does gain the proton to form the ammonium ion, and ammonium chloride is a soluble ionic compound. Ammonium ion is always soluble. So even though chloride is not always soluble, ammonium chloride is because it contains the ammonium ion. So it dissociates completely in a solution, and we see that chloride ion looks the same on both sides of our equation. So chloride is a spectator ion, which we remove from our equation. And our net ionic equation for this reaction is a proton plus ammonia equals the ammonium ion. All right. So how can we do this in general? In general, we want to have the same steps, essentially, as what we had previously. So again, we want to start with writing a balanced chemical equation for our acid-base reaction. Next, we want to identify all of our strong electrolytes, our strong acids and bases, and any soluble ionic compounds. So anything that is soluble based on our solubility rules. And then we want to write them in their completely ionized form. So that long version of the equation with everything as ions that can be dissolved as ions. And then we want to identify our spectator ions. And then we remove our spectator ions, and everything else that's left is part of our net ionic equation. All right, so here's another version of an acid and a base. So sulfuric acid and potassium hydroxide. These are both strong, so strong acid and a strong base. They're both strong electrolytes. So they completely dissociate. And if you remember, you can skip right ahead to what the end's going to look like, where you have a strong acid, strong base, net ionic equation. But we'll go through all the steps. So first, we write our balanced equation. So there, we're forming potassium sulfate and water. So potassium sulfate, potassium is a +1 ion, so we need 2 of them to balance out the sulfate ion, which means we need 2 potassiums on the right, which is where we get our 2 potassium hydroxides from. And that means that we have 2 protons on the left and 2 hydroxides on the left, which means we're going to make 2 water molecules on the right. All right, so we have our balanced equation. It's 1 molecule of sulfuric acid plus molecules of potassium hydroxide reacting to form 1 molecule of potassium sulfate and 2 molecules of water. And now we want to write our completely ionized reaction. So, like I said, strong electrolytes, strong acid, and strong base, they dissociate completely. We end up with 2 protons, sulfuric, 1 sulfate ion, 2 potassium ions, 2 hydroxide ions. And then on the right, we look at our potassium sulfate molecule. So sulfates are generally insoluble, but we have some exceptions. At least, well, let me check that before I say that out loud. I lied. Most sulfate salts are soluble, and the exceptions in this case do not include potassium, because potassium is one of our cations that is always soluble, one of our group 1A elements. All right, so that means that potassium sulfate is soluble. It is a strong electrolyte. It completely dissociates into sulfate ion and potassium ions. But water is a liquid molecule, so it stays intact. So our spectator ions are in red, sulfate, potassium, sulfate, potassium. They're the same on both sides, so we can get rid of them. And we're left with our net ionic equation for almost all strong acid, strong base equations, or reactions. Proton plus hydroxide equals water. In this case, we have 2 of each of those species because of our balanced equation. All right, so let's practice. So we want to write a net ionic equation for the overall reaction between sodium hydroxide and carbonic acid. So we have sodium hydroxide and carbonic acid. So these are both aqueous solutions. And we are forming, let's see, we're going to form sodium carbonate. So carbonate, a 2 minus polyatomic ion, and sodium is a +1. So to balance out our carbonate, we need 2 sodiums. All right, and what else are we going to have? So we had hydroxide with our sodium, and we had proton with our carbonate. So we're going to have water. All right, now are we balanced? So we have 1 carbonate ion on the right and 1 carbonate ion on the left, so that's good. We have 1 sodium on the left, but 2 on the right, so we need 2 on the left to balance that out. All right, so that gives us 2 hydroxides and 2 waters, which is going to give us 2 HOH if we just add them together. So that means we need 2 water molecules. All right, so our balanced reaction is 2 sodium hydroxide molecules plus a carbonic acid molecule reacting to form sodium carbonate and 2 water molecules. Okay, so now we're going to see if any of these are strong electrolytes. So sodium hydroxide, so it's a strong base. So it's going to completely dissociate. So we're going to have 2 sodium ions and 2 hydroxide ions. What about carbonic acid? So carbonic acid is one of our weak bases. It's an organic base. It's weak. So it does not fully dissociate. So I'm going to keep it together. Just like we did with our ammonia in our weak base strong acid problem. Okay, and then we're forming sodium carbonate. So carbonates are generally insoluble, but sodium is an exception. Sodium is one of our cations that is always soluble. So we're going to have that fully dissociate as well. So that's 2 sodium ions and a carbonate ion. Okay, and then finally we have water, which is a liquid, so it stays together, not an aqueous solution. All right, so what do we have that's the same on both sides? We have sodium ions, so we can get rid of those. And what do we end up with? We have two OH ions, two hydroxide ions, plus our carbonic acid, which does not fully dissociate, so we leave it alone. And we're forming a carbonate ion and water. We can't cancel anything else out because we need everything else in either the left side or the right side of our equation. So that is our net ionic equation. So you see, when we have the reaction of a strong base and a weak acid, or a strong acid and a weak base, we don't always end up with our proton plus hydroxide equals water equation. We have some extra stuff because we don't have full dissociation. Okay, so I'm going to end here and we'll talk about gas forming reactions.